Okay, so how is everyone today? Good, I hope? All right, I need to turn that light off. Okay, just a second. All right, so was the quiz everything you hoped it would be? Yeah. So we didn't do any new material on Friday because we were doing the quiz thingy. The last new material we were talking about was Wednesday, and on Wednesday we were talking about radicals. So we're going to pick that up. Not 8, 9, right? And then today's the 4th. So specifically, last time, here's a summary of it. So these things are called radicals, and they are also known as roots, like square root and cube root. So to recap what we said, we defined square root. So the definition of that is let x and y be in the reals. Then the following are equivalent. So the first condition is that y squared is x, and y is greater than or equal to 0. So that's the first condition. And that condition is equivalent to the next condition. So, that's y with exponent 2. And the way we usually write that is just a superscript 2, right? But if you desired to write that with punctuation, then the way you'd write that is caret 2. And if you want the caret 2 to switch sides to go to the other side, then that would you could say that if you want to solve for y, then the caret 2 switches sides and it looks like this when it does it. So that's like that. And this is called square root. Right. Now my experience tells me that this inequality is the most overlooked bit by students. It's the most overlooked bit. So, concerning the square root, note the input and output are non-negative. So now a couple things is that first, the phrase non-negative feels a little clumsy until you're real sure about its meaning. At the beginning, a lot of students think, why is it saying non-negative? What's wrong with positive? No, there's nothing wrong with positive, but non-negative and positive aren't the same thing. What's the difference? Yeah, 0. Okay, so 0 is non-negative, but it's not positive. So non-negative means 0 or positive. And the input and the output to square root have to be non-negative. That means that it's not okay to put negatives inside the square root. That's not allowed. And it will never be the case that you evaluate a square root and the result is negative. That'll never happen. There'll never be a negative output. All right. Then immediately, more or less immediately after that, on Wednesday we defined cube root, where we said, well, it'd be nice if instead of just doing this with a 2 there, what if we do it with a 3? So now it's let x and y be in the reals. The following are equivalent. First, that y cubed is x, So notice that I took exactly that equation, but instead of using exponent 2, I used exponent 3. Now, in this situation, there is no corresponding inequality. I'm not forgetting it, but I'm going to just literally write here, there is no inequality here. To emphasize that there's not one there. I didn't forget it. It's just in there. Doesn't exist. If we want to solve for y, then we want this caret 3 to switch sides. And when it switches sides, it visually looks similar to square root. Now, what I've written currently is exactly square root. So we can't go with this. This wouldn't work. You can't write them the same way, because then it would be confusing, right? You wouldn't be able to tell, wait, is this the one that's 3 or is it the 2? So the way that you denote that this is the one with the 3 is you write a 3 right there. So it's sort of like that's a little hand that's, you know, like holding up the 3, you know, like over there, like, you know, here I am holding up the 3 there, like that. And so square root in history, you know, where in the historical events, square root was the first one, you know, and you know, that individual didn't plan ahead, you know, so it was just written this way. And then, you know, when people started saying, yeah, what about with the 3 there? then okay, I'll put the 3 there. So for that reason, with square root, you usually don't write the 2, but you can write the 2 for emphasis. Say, like you know, if you just really wanted to emphasize that we're talking about square root here, you could write the 2. Okay. Now, you know, we did it with 2, we did it with 3. In fact, we can do it with any natural more than 1. So here's the general case. This is just called nth root. So what I'm saying is that this one is the case for n is 2. This is the case for n is 3. And this is going to be the case for any n. But what we'll observe in the case for any n is that the behavior will be split into 2 categories. Those that are going to act, you know, largely like square root, and those that are going to act largely like cube root. And the distinction is going to be whether or not n is even or odd. So you can think of square root as like the prototype for the even case. And you can think of cube root as like the prototype or the odd case. Okay, so now the definition is let x and y be in the reals. And now we want n, little n, in the naturals with little n more than 1. The following are equivalent. So now, to explain this new bit, all we're saying is that we're going to consider any natural that's more than 1. So what are the naturals then? What is the set of all naturals? You remember?
All non-negative integers.
All non-negative integers, which means that it's the integers starting with 0. So 0, 1, 2, 3, 4, going on. So if we say a natural that's more than 1, what that's saying is that, well, any natural except 0 or 1. We're not going to have that. No, 0's out, 1's out, but 2's okay, 3's okay, 4's okay, 44's okay, etc. All right. So now to make the general definition, we need 2 columns. Because we're going to have 2 cases. the even case and the odd case. So in the case that we have an even n, that'll be on the left. And in the case that we have an odd n, that'll be over here on the right. So the following are equivalent. Y to n is x. And remember that square root is the prototype for the even case. So we're going to need that inequality. Y to n is x, and y is greater or equal to 0, like square root. And then this is equivalent to y is nth root of x. Okay, in the odd case, we'll have y to n is x, and because that's n and n equal 3 is the prototype for the odd case, here we do not have an inequality, so no inequality. And then solving for y, like so. Now, concerning inputs and outputs, the even case is like square root. So for the even case, the input and the output are non-negative. Now, I didn't explicitly mention it for a cube root right here, but what about inputs and outputs for cube roots? Is there any restriction on the inputs and outputs? There isn't, right? Not in the odd case. All right. So now let's calculate a little bit. So for example, how about the fifth root of negative 64? Okay. So in my mind, the first thing that pops out is that, okay, we're talking about a radical. I can see this square root looking symbol. That thing's called the radical symbol. And I can see that the input is negative. So the fact that I have a radical and I can see that the input is negative, in my mind, the very first thing to check is to ask, is that even defined? Is that a thing? So yes, we can do this input. Why can we? Yeah, because this is fifth radical, and 5 is odd. So, is it defined? And the concern is a negative input. So the answer is yes, because 5 is odd. So we're in the odd case. Okay. So we'd like to simplify this. All right. So in order to do that, we're going to need to factor negative 64 as best we can. So for the purposes of like test taking, it would be a really good idea for you to memorize some certain things. Like it would be good for you to memorize the squares of all integers as far as you can go, like 0 squared, 1 squared, 2 squared, 3 squared, all the way up to like 25 squared. Just you need to know them all. Same with cubes, that would be good. Fourths, if you can do that. Even I have trouble with that one. Powers of 2, you should know powers of 2. As far as you can go, at least all the way to 2 to exponent 10. The reason why is because those just simply come up a lot in math and science and in math classes. And as it happens, 64 is a power of 2. What is it? 2 to not 8. Well, let's think about it. 2 times another one is 4, 8, 16, 32, 64, right? So 64 is 2 to 6. So we could say, all right, this is 5th root of negative 2 to 6, like that. So we factored it out. We factored it a little bit. All right, and now I'll say this. This is now what that is that's 6 2's all multiplied together. So there's 6 of them. So what I'm going to do is I'm going to say that I'm going to interpret this like this. That this is negative, and then there's a single 2, and then here's 5 more of them. All right, so you can see that all 6 of the 2's are accounted for. There's 1, and there's the other 5. Okay. Now, what 5th root does, just like square root, if I ask you what's the square root of 16, then the answer is 4. The reason is because 16 factors as 4 times 4. So that's a pair of 4's, and so they come out of the square root. The reason why you need a pair of 4's is because square root is radical number 2. So when you're simplifying square roots, things come out as twins. When you're dealing with cube root, things come out as triplets. When you're dealing with 4th root, things come out as quadruplets. And when you deal with 5th root, things come out as quintuplets, right? Groups of size 5. So what I'm saying is like here's a quintuplet of 5, a quintuplet of 2's. Here's 5 of them all together. 2, 2, 2, 2, 2. This factors out as just a single 2. So, that would be 2, and then multiplied by the 5th root. And then now, what was left inside? The negative 2 was left inside. Okay. Any question about this? So now here's another one. We can continue doing this. We can say, all right. Now I can interpret that negative 2 as 2 multiplied by the 5th root of say negative 1 multiplied by 2. Because after all, that's the same as that, right? And now I'm going to do a trick. And I'm going to say that, all right. So if we had negative 1 squared, then the negative would square away, right? And we'd have 1. And if we did negative 1 to exponent 3, then we'd have 3 of those negative 1's. Right, and then you could take a pair, and those would simplify to 1, and you'd still have that negative 1 left over. And then negative 1 to 4, that'd be 1, right? And then negative 1 to 5, negative 1 to 5, that'd be negative 1, right? So generally, the rule is going to be that negative 1 to n is going to be 1 when n is even. So, something like negative 1 to crazy number, right? 1314. What's that going to be? That's 1, right? That's 1 because in the end, 1, 3, 1, 4 is even. Whereas, negative 1 to 2019 is what? Negative 1, because we have an odd number of them. So what I'm saying is that, okay, there's that negative 1. There's that negative 1. And I'm going to say, okay, here's that 2. So that 2, and then multiplied by 5. And then instead of writing negative 1, I'm going to write negative 1 to 5 times 2 like that. And now, where we had just one negative 1, now we have a quintuplet of negative 1s. So what can I do with this negative 1? It can come out, right? It comes out as negative 1. So that would be negative 2 like this, times the 5th root of 2. Interesting. Any question about this one?
And
Yeah?
having the negative sign on the outside of the radical is considered the proper simplified way?
Yes.
Okay.
Other questions? All right. So, now, another thing that we talked about on Wednesday was absolute value. And just to recap what that was, is that we said, given a number, we want to say what the absolute value of that number is. And the absolute value of 0 is 0. So you can take that as definition. And then for any number that's not 0, the real numbers always come in pairs in the following sense, is that, there's 2 7s. There's the negative 1 and the positive 1. And there's 2 pi's, the negative 1 and the positive 1. So if I ask you about the absolute value of x and x isn't 0, then the answer is the positive version of x. So the absolute value of 10 is 10, the absolute value of negative 11 is 11. Okay. Now the place that comes up in the context of radicals is that radicals almost undo things, but not exactly. So here's what I mean. So suppose we have a y, and then we multiplied that y by 3. Now if you said, nah, actually I thought about it and I don't really want to do that, I want to undo that, then how do you undo it? What's the undo for multiply by 3? Divide by 3. So what I'm saying is that if you wanted to solve for y, then what happens is that this multiply 3, where equations are concerned, switches sides and becomes that divide by 3. So the undo for multiply by 3 is divide by 3, and vice versa. Similarly, we can say something like, p minus 4 is q. So what's the undo for subtract 4? Add 4. So you could say p is q plus 4. So subtract 4 and add 4 perfectly undo each other. And the thing is that radicals, you kind of would like radicals to have similar property. So like you kind of like squaring and square root to perfectly undo each other, and cube root to undo each other, and exponent 4 and radical 4 to undo each other. You might kind of like that, but that's in fact not the case, not entirely. Okay, the reason why it's not the case, not entirely, anyhow, is that we've broadly classified radicals into 2 groups, the even and the odd kind. Okay, so we've got the even kind and the odd kind. And then concerning radicals, concerning 2 operations, you can ask what order did they occur in. So for multiply and divide, it doesn't matter what multiply by 3 and divide by 3. It doesn't matter what order they occur in, right? So then divide by 3 followed by multiply by 3 is a nothing, and so is multiply by 3 first and then divide by 3. That's also nothing. So those perfectly undo each other. But with radicals, that's not the case. So we need to consider two orders, and we need to consider even and odd. Okay. So there's two things to consider. Two items to consider. Do we do the order? So do we do exponent first? Then nth root? Or do we do nth root first, then exponent? So that's one possibility. And the other possibility is parity, which is to say even or odd. So now, if there's two choices, if there's two decisions to make, and each one of them has two possibilities, then altogether, how many combinations are there? There's four, right? It's this order and even, this order and odd, this order and even, this order and odd. So we have to have four different possibilities. So now we're going to make it. I'm going to make a 2x2 table that's the rest of the size of the page here. Order, parity, so on the first row, that'll be the even row. So n is even. The next row, n is odd. The first column will be the order where we do exponent first. Then nth root. And the next column will be nth root first. Then the exponent. All right. So there's four possibilities, and three of them are going to be the same, in a sense. But this one out of four is going to be the odd one out. the strange one. I don't want to say odd because I'm already saying even and odd. This is going to be the strange one, the one that's weird. Okay. So if we're going to do exponent first and then this, that means that the expression we're looking at is this x to n. So we do the exponent first, and then we do this. And the question is that do they simplify? And the answer is no, they don't. They don't, because you'll remember last time we talked about what's the square root of x squared. So what I was asking is, well, what if you take an x and you square it, and then immediately after that you compute square root? Then what do you have? You have the absolute value of x. Not x. So those absolute value bars cause a lot of people, a lot of folks, a lot of problems because they're easy to forget. So now, to persuade you that that this really is the case, it really does happen this way, is something like this. So example. Suppose we start with, say, -3. And then we take that -3 and we raise it to exponent 4. So raise it to exponent 4. So that'd be -3, -3, -3, -3. So if we take the first two and multiply them, -3 times -3, that's what? 9. And we take the last two and multiply them together, that's another 9, right? And then that means, so if you take all 4 of those -3s and multiply them all together, you get 81. So now, we get exponent 4. Now if we follow that up with fourth root, well, what's the fourth root of 81? 3. So observe that first you did exponent 4, then you did radical 4. And it didn't undo, right? You started with -3 and you ended with 3. And there's nothing special about -3. If this had been a -33, then this one would be a +33. So what kind of thing is it that when you put a negative thing in, out comes the corresponding positive version? Well, that's absolute value. Okay. Now, if we do exponent first, but the exponent is odd, then this still looks the same. So nth root of x to n. But now what? Does it do those cancel? They do, actually. It actually does work. It actually does work, and remember, that's from last time. Last time we said, well, the cube root of x cubed, for example, is just x. And to see an example of that in action, the problem is when you start with a negative input. So -2, suppose we take a -2 and we cube it. Well, what do you get if you cube -2? You get -8, right? Notice that the negative doesn't squash, doesn't get crushed. It's still there. And then if we immediately give that to the cube root, well, what's the cube root of -8? -2. So do you observe that we start and end with -2? All right. So now this column is when you take this machine. I'm kind of viewing this like an assembly line, right? Like first this, then that. First this action, then that action. This other column is where you say, well, let's take these and then let's put them in the other order. Let's do the radical first. So now the expression looks like this. So now it'll be, okay, radical first, and then this. So you can see they look similar, but here, for this one, this new one we just wrote down, the radical is happening first and the exponent is happening last. So what about this? Does this simplify? It does. It does, even though this one is even. It's still going to simplify. And I'll write more there, but here, I'm going to go ahead and write this one too. Here the expression is this. So nth root of x to n. This one also simplifies. So notice that there's 4 possibilities, and this is the stranger. All the rest of them work. Nevertheless, this one comes up so often that this is a real, it's worth my time, and I estimate it's also worth your time for me to be up here droning on and on and on about it. Did I see a question somewhere? Did you have a question? Which one?
Each expression.
They're not, because see, this one, see, that's radical is on the outside, right? Whereas this one, exponent is on the outside. So they're not the same. Oh, did I make an error somewhere? I can't. This?
Yes.
This one? Yeah, they should be the same. So yeah. What I'm saying is that this one, in this column, this is the same. So this, same as this. So you might say, I don't know. I guess I see why this one has to be absolute value, but why not absolute value here? Well, let's take this example right here, and let's start copying it down. But let's just change the order of the things that we're doing. So what if we say, okay? So here's an example. If we say, okay, the first thing we're gonna do is exponent 4, and we're gonna get something, and then after we do exponent 4, we're gonna do radical 4 and get something. Okay. No, that's it. Sorry, I copied it exactly. I meant to write those in the other order. So now, just to verify that a positive input works the way that you hope it would, suppose we start with, say, 16. Well, what's the fourth root of 16? It's 2, right? Because 16 is 2 times 2 times 2 times 2. And then what if you do 2 to exponent 4? What do you get? 16. So that works as expected. But then you might say, but what about the negative one? I bet something, something tricky. So then let's change it to negative 16. This and this. And now, what about this? You can't do it. Now, because you're not allowed to do it, that means that it could not be the case that you get here and this isn't a negative 16. It can't be the case that you get there and that's a negative 16 because you can't get there. So this is impossible. So the impossibility of it is what makes the simplification work. So impossible. All right. So there's 4 possibilities. That is when absolute value shows up. Good. So now let's do a little bit of simplifying. But we need one more thing, actually. Is that, so this kind of expression will start showing up with frequency now. So we could write x, absolute value of x times absolute value of x, something like that. So this kind of thing can show up. And, all that matters is it's that thing and then that thing again. So it's repeated, right? So then that means that we could write this more simply like this. So that thing repeated twice and multiplied. We could also say something like, well, how about absolute value of z multiplied by absolute value of z multiplied by absolute value of z? So what's a nice way to write that? Right, absolute value of z, and then cube that. So that's nice. Now, I'm just showing you that the absolute value doesn't change this exponent notation that we already have. But here is one thing, and that is the following simplification, is that we can write the absolute value of x to exponent n, 2, 3, 57. Okay, this is equal to regular old x to exponent n, which is to say that you can simplify away the absolute value when n is in the naturals, n more than 1, and n is even. So, to explain, how about the absolute value of y squared? What I'm saying is that you could write this as just regular old y squared. You don't need the absolute value. Now, the reason why you don't need the absolute value is we can illustrate it with a specific example. So how about the absolute value of -5 squared? So, okay, because absolute value is closer to the -5 and the exponent is outside, that means we need to deal with absolute value first. So, ignoring the square for a moment, what does absolute value of -5 do? What does it become? It becomes regular old 5 squared, right? So 5 squared, which of course is 25. Now, what I'm saying is that suppose that we just forget the absolute value, we just drop it, and instead of looking at it as absolute value of -5, suppose we just look at it as -5 squared, so that we don't have the absolute value. Well, what is -5 squared?
5.
It's 25. The negative squares away. Would this work? Absolute value of w to 7 is w to 7. Is that right? That's not right. It's not right because in the end 7 is odd. Okay. Now that we have that out of the way, we can consider the following example. So here's a relatively straightforward example, just for you to get the flavor of it, and then we'll do the one that I really want to do. How much time do we have? Yeah. So 16, and then I'll say something like x to 7, like that, and then how about y squared, and then z to, you know, whatever, 37. Okay, so then what we want to do is simplify this. We want to simplify this, and we want to simplify this with the following rule. So simplify with the rule that the nth root of a multiplied by b is nth root of a multiplied by nth root of b. So this works. You can use this rule when both are defined. Like that. And just to try and forestall any serious problems, so what this is called, this is the distribution of radical over multiply. So now, you know, last week we were saying, okay, we've got 3 operations, add, and then repeated add is multiply, and repeated multiply is exponent. And then we had 2 distributions. We said that multiply can distribute over add, and what else did we say? Yeah, exponent can distribute over multiply. And then the big error is to try and do what? Right, to try to do exponent over add. The corresponding big error here is to try and do radical over add. Radical over add doesn't work. So, that being the case, what we want to do is make groups of size 3. So, writing this as simply as possible. So, 16, well, that's 4 2's all multiplied together. So, I'll say that that's 2 to 3. So, there's 3 of them. And then there's one more. Don't forget that one. And then now, if you have 7 apples, how many groups of size 3 can you make? 2 groups, right? So then I'll say that here's 3 x's, and here's 3 more, and then there's that last one. So there's all 7 x's accounted for. And then how many groups of size 3 can we make from 2 bananas? None, right? Can't make any groups. So I'll leave, that's y squared, and then I'll leave the z's for a later step. And what I want you to observe is now, okay, that triplet of 2's can come out as what? As a 2. That triplet of x's can come out as an x. And that triplet of x's can also come out as another x. Okay? So you could write this as 2 multiply x multiply x multiply. And then now cube root of what? So what was left over? A 2 was left, an x was left, and that y squared was left. And then we have z to 37. Now, we could slowly take out a group of 3 z's, right? We could take out a group, there'd be a z, and then there'd be 34. Right? And we take out another group, there'd be another z, and now in here there'd be 31. And take out another group, just keep going, right? But in the end, you just need to ask, well, if I had, 37 soccer balls or something, how many groups of size 3 could we make? 12. That would account for 36, and then there'd be 1 left over, right? So what I'm saying is that because 37 is 3 multiplied by 12 plus 1 more, that means that we can say that this is 2 multiplied by x multiplied by x multiplied by z multiplied by z multiplied by dot 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 multiplied by z multiplied by the cube root of 2x y squared, and there was 1 z left over, and here there are 12 of those z's. So of course the simplest way to write this is something like 2x squared z to 12 multiplied by cube root of 2xy squared z. Now have a look inside the radical. What we did is we repeatedly pulled out triplets, right? We pulled out a triplet of 2's, we pulled out some triplets of x's, we pulled out lots of triplets of z's. And concerning all the stuff that's left in there, now there's more than 3 things left in there. But is there any triplet that's left in there? No, right? There aren't 3 x's to be had. There's 2 y's, but 2's not enough. We need 3. So can you see how it works? So the last thing that we'll briefly mention at the beginning of next time is that, okay, what if instead of using an odd radical, if we were using an even radical? So instead of like 3, what if we were doing 4? Then first difference is that quadruplets would come out. But there's another difference, is that x to 4 would come out as not x. What would it come out as? It would come out as absolute value of x. So that's one more bit of bookkeeping that we'll have to keep track of, and we'll talk about that on Wednesday next time. So have a nice Monday.